Okay, guys, I think we can get started. Well, today I'm going to talk about Energize multi-tenancy Flink on Kubernetes with YuniKorn. You probably noticed that there are several keywords here for this session: multi-tenancy, Flink, Kubernetes, and the Unicom. So we're going to cover these topics today. My name is Weiwei. I am a staff software engineer from Cloudera, and I'm also a Hadoop committer and PMC member since 2017. And before joining Cloudera, I was working for Alibaba and IBM for a couple of years. And when I was working at Alibaba, I actually was in the Alibaba Flink team. So where I had some experience running large-scale Flink on YARN. Wilfred is my colleague, and he works closely with me on the project we're working on. And he's also a staff software engineer from Cloudera, a Hadoop committer. Before Cloudera, he was working for Sun and Oracle for a couple of years. But unfortunately, Wilfred cannot make it today because he's located in Australia. It's like 3 a.m. in the morning for him. So I will be the only presenter today. So first section is about Flink and the Kubernetes. The rise of Kubernetes. I think if I would say Kubernetes is the de facto of the container orchestration framework, nobody will disagree. So this is kind of standard for now. I think there's a lot of advantages when people use Flink, use Kubernetes. Like I am not going to list all of those things here, but for 5 important things I want to highlight is the first one is modularity. So basically, I think Kubernetes did a very good job to modelize the components, like the runtime, the network, the storage, and to make them highly pluggable. And people can have many flexible abilities to customize things, which is great. The second thing is it is highly pluggable and extensible. So this is something I really like. In Kubernetes, we can define customer resource definitions. We can define our own operators to manage the software lifecycle. We can also apply a lot of plugins, which is super flexible. And the third one is the software lifecycle management. So it is so easy to manage software lifecycle in Kubernetes, if it's comparing to YARN. And also, it has some advanced features, like it has the self-monitoring, self-healing. So these features, DevOps are loving them. Also, one more important thing is the large community and the strong ecosystem. So you have so many users using it, so you will never feel alone. For me, I think more importantly, Kubernetes give us the opportunity, right, to allow us to build a modern, unified infrastructure framework for on-prem, on-cloud, hybrid cloud, and multi-cloud. You can see there are a lot of vendors out there to provide solutions based on Kubernetes for their on-prem solutions, on-cloud, public cloud, and also hybrid cloud, like us in Cloudera, and also multi-cloud. So people can. So ideal case, so people write their code, write their applications, then you can run everywhere as long as the infrastructure layer is Kubernetes. So this is super important for customers, for clients who want to use Kubernetes. I think that gives us a strong reason to move to Kubernetes, right? So it sounds like a perfect zoo for Hadoop animals. You know, as a Cloudera, we are seen as a Hadoop company. We have so many open source components where we have ADF, have YARN, have MapReduce, Hive, Kudu, Impala, Spark, Kafka. So those components, will that fit into Kubernetes? So this is the kind of question we were thinking about more than 1 year ago, and we start to move some of the things running onto Kubernetes. And we thought it would be a very good experience, also the right direction to go. So, and even for Flink. So last year, Cloudera announced that to support Flink in our offerings. So for Flink, we also think about to running Flink on YARN, on Kubernetes. However, I think actually is really that perfect? Yes and no, I would say. People realize that the target is to move to use a simplified and unified platform using Kubernetes for every use for their applications. However, to get into that target, well, it might be a little more work than you can imagine. Talking about the challenges. So today, since we are talking about Flink, we are majorly talking about the challenges Flink on Kubernetes. As you should know, Kubernetes is designed for long-running services, but for Flink, it's kind of a mixed-type workload. Why I'm saying Flink is a mixed-type workload? I think you probably know there's a very popular slogan in Flink: batch is a special case of streaming, which I really love it, right? So Flink is the purpose of having Flink engine is to provide a unified process engine for both various of scenarios. So you will contain the long-running stream jobs. It also have the interactive queries, probably short-lived jobs, which means the Flink workload itself is quite complex. If we want to move such workloads to Kubernetes, we are facing more challenges than other engines. If we consider about how to guarantee the SLA, how to enhance the latency, how we improve the multi-tenancy, how we make sure every team runs their Flink jobs in a shared cluster efficiently. So those issues, those challenges we are facing those challenges when we start to move Kubernetes. This is the main thing we want to focus on for today's topic. For Flink on Kubernetes, so first I think we need to look at the Flink on YARN to understand how it works. So there are two main fashions. First is the per job. The second one is session. And for per job mode, it basically leverages YARN containers. When we submit Flink jobs, and it will launch several YARN containers. One of them will be the application master. The rest of them will be the containers to run task manager. And when the Flink job is done, the cluster, the containers are gone. And when submit another job, we need to recreate those things from the beginning. So in this way, we have good isolation, but the latency could be a problem because every time we have the delay, we have the overhead to create containers, and after the job is done, we need to tearing down everything. So if we have a strong latency requirement, sometimes this will not need to be improved. So there's another mode is session. When we use session mode, we were running a shared job manager service running in a central container. And then we launch a number of task managers, and each of them will be able to run one or more task slots. And the subtasks of the Flink jobs will be running in the slots. So in this case, we're sharing the task managers. We avoid the overhead of recreating the containers, everything. So it will help the latency, help to resolve the latency problems. So both of the fashion is pretty popular in the real world deployment. And this is the first thing we need to understand, because on Kubernetes, we are having the same patterns. Flink on Kubernetes today. So as you might already know, there are three major flavors to run Flink on Kubernetes. The first one is standalone, which supports the per job and the session deployments. It's very simple. It leverages the Kubernetes deployment, the service, those native things with the predefined number of job manager, task managers. So it's kind of a static deployment and very simple to start. There's another way is the Flink on Kubernetes operator. So this is our operator approach where I think it's more lateral because in Kubernetes, when you work with Kubernetes, the way you work with it is with the resource definitions. So with this approach, you can define the job managers, task managers with Flink cluster CRD, and you submit that CRD to the Kubernetes cluster, and there will be an operator running behind this. It will manage the Flink cluster lifecycle for you based on the definition you gave in the Flink cluster CRD. So this way you can keep monitoring the status from the native and general API Kubernetes exposed to us. Very easy to interact with. But I mean, this is more a Kubernetes way, but it's not perfect. So there's another approach, which is a new feature in 1.10 release. This is the active Kubernetes integration. So the main difference for this approach comparing to the Kubernetes, to the operator approach, is this one actually implements a resource manager for Kubernetes, just like what it does for YARN. So it will natively talk with negotiating with Kubernetes API server, asking for ports or deleting ports. And so everything is done through the internal native channel. And it has more understanding about the Flink job context. And moving on, it will be easier to support auto-scaling. Ideally, this approach should be more efficient, and this is also the approach used in Alibaba. They are using the active integration to be able to efficiently use the resources in the cluster. So, but I would say this is an advanced fashion comparing to the rest of the two. Given we have so many, we already have these approaches to run Flink on Kubernetes. Is running Flink on Kubernetes easy? I would say no, because when you move your production workloads on Kubernetes, you're facing a lot more problems than just running them. And the one particular thing is about the scheduling challenges. So the resource scheduling in Kubernetes has a lot of limitations. It doesn't have the first-class application concept. It doesn't have the fine-grained capacity management. It doesn't have the job ordering. It doesn't know the jobs at all. And it doesn't have the resource fairness, which is a very, very important concept for the batch workloads. It doesn't have the data locality. But I think the trend is to use the disaggregated storage and the compute. This is less important, but still some people want data locality. And there are also some throughput scheduling latency problems. This is due to the fact that the scheduler in the Kubernetes is not designed for such scenarios. It is majorly designed for long running. The workflow is very simple. So every time scheduler picks up a pod, find the best fit node, and then run that pod on that node, nothing else. So this leads us to so many limitations. We're having so many issues when run Flink on Kubernetes. That's why we are proposing a project, which is YuniKorn. So YuniKorn is an RPG incubator project. It is created to resolve the scheduling problem for Kubernetes. So it is a resource schedule for Kubernetes, but the design is we are not limiting us to just support one platform. It's a general resource schedule can support multiple platforms. And second thing is it has the built-in capabilities to support both long running and batch workloads. When you have such scenarios, you can consider about using Unicom instead of a default scheduler. And moving on, I'm going to talk about more about what we have in Unicom. First thing is, the first thing to understand is the Unicom is a stateless service that runs in a pod. As you can see that it can be deployed as a pod running in the Kubernetes cluster. It tells the API server to manage the pod scheduling and allocation, just like the other schedulers. It can be used as a secondary Kubernetes scheduler if you want to try out or explore things with YuniKorn. You can use the secondary scheduler running in the same cluster. or it can be user replacement for the default scheduler, because we have built in the full functionality that default scheduler supports. I can go to details about that later. We just look at how default scheduler works. Why we are saying YuniKorn can resolve the scheduling problems in Kubernetes. So here's how YuniKorn works. This is a very simple chart to demonstrate how the workflow inside of YuniKorn regarding to the scheduling. So first, people submit jobs to Kubernetes, and they will be submitting to YuniKorn queues. And inside of these queues, every time we will do a sorting to find out the best queue to assign resources to. And this is based on some policy like the resource fairness to ensure that each of the queue have the similar fair share of the usage. And then for the queue we select, there will be a list of jobs inside of it, sitting inside of this queue. Again, we'll apply another policy to find the best job to schedule. And this is we can leverage the policies like FIFO or fair policy, and based on these policies, we find the best job, then find out the job requests. So the requests are the outstanding, which is are the outstanding pods. Then we will based on the priority of the pods, and we can find the most important requests. And then on the other hand, we have a bunch of nodes. This is the nodes the cluster has. We do a node sorting based on the scoring mechanism, which is also pluggable. So we can find out the best node for the request. Then the final step is to allocate the request to that node, bind the pod, bind the volume, and everything else. Then it will be the pod will be scheduled on that node. If you remember the workflow that default scheduler has, it only has the major differences. The default scheduler only handles this part from the requests, which is a bunch of pods, find the request, bind it to node. But it doesn't have any concept about the queues, where the queues defines the fine-grained capacity controls. It doesn't have any idea about the jobs, and the jobs is important where you want to, when you do the scheduling, you want to understand the jobs and you want to schedule based on the jobs. So these things are missing, and this is the major differences we have. Some highlight features in YuniKorn today is first, we have the application as the first-class citizen, which means if you run Flink job, it will be an application. And we treat it as an application, and we schedule it as an application. And another thing is it supports job ordering. It has we have the FIFO policy, and we have the fair policy, so those can determine the ordering when we want to schedule the resource for them. And another one is the hierarchy queues. And this is to have you to ensure that you have fine-grained control on the resource management. So basically for a big cluster or complex use case, for a multi-tenancy environment, you probably want to define your queues in a hierarchical structure. So you can map your team, your groups to several live queues. Then we can manage several levels of resource quotas easily. And also, we have the load sorting policies. We have the fair and the bin packing, different two policies. I can explain that later. And we have better performance. So to improve the performance, we have done a lot of work to make sure that the scheduler throughput can be improved a lot comparing to the default scheduler. And we have provided a central resource view. It's a management console. You can view the resources, view the applications. I can show some details later. To run YuniKorn on Kubernetes is very simple. So we have the Helm chart. Simply do a Helm chart install. you will have YuniKorn on your cluster. There are two modes to run YuniKorn on the existing Kubernetes cluster, which is one is exclusive, the other one is share. So when we say exclusive, which means the YuniKorn schedule will take over the cluster. The default schedule will be idle. And to do this, we have a YuniKorn admission controller along with the deployment. Once the admission controller enabled, it will help us to route all the traffic, all the pods to YuniKorn scheduler. You don't have any setup in people's in users application, zero modification on the application side, and all the pods submitted to Kubernetes cluster will be handled by YuniKorn. So this is the exclusive way. We're using this way in most scenarios, but there's another way is the share environment, which you can run because Kubernetes supports to run multiple schedulers, and we can run YuniKorn scheduler side by side with the default scheduler. But there's an approach to divide a cluster to separate them for each of the scheduler. But this is not this is not a must. So you can also run YuniKorn together with the scheduler. We have some logic in YuniKorn to recognize the resources being scheduled by other schedulers. So it should work. If you want to do some experiments or explore the features of YuniKorn, you are perfectly fine to go this way. It doesn't have any impact on the existing jobs, existing applications. But if you want to leverage YuniKorn, simply run some pods and point that to YuniKorn scheduler. That will help you to explore things. Then run Flink with YuniKorn. Today, if you are not using admission, if you are using admission controller, there's nothing you need to do. Everything will be handled automatically by YuniKorn. But if not, you will need to specify schedule name to YuniKorn in the pod spec. So YuniKorn knows that this pods with this label will be scheduled by YuniKorn. And in the standalone and active mode, so YuniKorn supports both scenarios, both fashions like we mentioned earlier. There are three approaches to run Flink on Kubernetes. For standalone active, we just simply need to add a label to identify the application ID. This is how we identify the applications, the jobs in the Kubernetes cluster. This is the only thing needed. And if you are using the Kubernetes operator approach, which is also simple, we just need to add a plugin to YuniKorn to recognize the Flink cluster CRD. So this plugin doesn't exist today because we are using the active mode working in some of the Flink clusters. But the operator approach is also simple. You just need to, I think maybe just 109 of the code. You will get a plugin, and you should be able to manage the Flink cluster CRD easily in YuniKorn as well. Then next section, we will talk about resource scheduling with YuniKorn and how it will help with the Flink scheduling. First thing is for people using Kubernetes, I guess everybody is using namespace. So in YuniKorn, this is also a very simple and very straightforward setup for us. So when we work with your namespace, everything you are using today in the namespace is continue to work. There's nothing changed. But if you have enabled YuniKorn in this case, besides the namespaces you have additional things like I demo here. So a simple example is how you can work with YuniKorn with the namespace is you submit with 2 ports, and each of them are in a namespace. So this part is Kubernetes is still using the quota admission controller to say if the pod will go beyond the resource quota defined for this namespace. If not, admit to the scheduler. So this part, if we replace the scheduler with YuniKorn, this part will be handled by YuniKorn. So every pod when it comes, we check if there's a namespace, which namespace this pod comes from. Then we will set up an internal queue to map to the namespace. So like here, for two different namespaces, we're mapping 2 different queues. And then in the queue manager, we are automatically creating the queues. And then we're scheduling based on the queues, based on the applications, and then place the pod to the correct namespace. In this way, you don't have to set up any internal YuniKorn queues. You just continue to work with the namespace. We do the mapping automatically. And as a bonus, you get a resource fairness between the namespace, between these 2 namespaces. And you get a job ordering inside of the namespaces. And also you can define the pluggable load sorting policies to determine how you want the node to be selected for the pods. So you will have those things as a bonus, but you don't have to disrupt anything that is working today. And this is also the most scenarios we're using Unicom. Very, very simple. This is the configuration we set for Unicom. Basically nothing. You don't have to set up the queues because we're doing the mapping here. And you just set up a placement rule like this, and it will do the automatic mapping for you. You don't have to worry about anything. Job ordering, we talk about that too. And right now in Unicom, we support the FIFO ordering and the FAIR ordering. The FIFO is based on the job submission time, and the FAIR is based on the resource used by the jobs. So they will fall into different scenarios. If in some scenario, people are concerning about the orders of the job, then FIFO is perfectly fine. It's very simple, and you can use the FIFO policy to enforce that. And for some other deployments, especially when your class is so big, and you can enforce the FAIR. So the queues, when we schedule pods in jobs in the queues, we consider the resource fairness. Like I mentioned earlier, this is how Unicom organize a job. Basically, we just need a very simple label in the pod spec to let us know this many of the pods belong to the same application. Then we can enforce the job ordering for these pods. For the load sorting policy, it's very similar. So we support two fashions of policies. One is FAIR, which is actually means this is the chart for the FAIR policy, which means we want to evenly distribute pods onto the nodes. This is usually fit into the scenario you have a static resource pool. You have your Flink clustered in data centers, and this might be the right way to go. On the other hand, we support the bin packing policy, which means we, as the scheduler, we aggressively to bin pack the request into less number of nodes. So we'll see the nodes is being heavily used one by one. And this is suitable for the scenario when you have elastic resource pool, which means when you run Flink on cloud, and usually you leverage the autoscaler to scale up and down your cluster. So in this case, you want to have the resource utilization for each of a node more than use as much of resource for each of the node before scaling out another one, right? And also for scale down, it makes sense because in this deploy model, you can constrain your footprint in a small subset of the nodes. Then you can have some idle nodes, so the autoscaler can decide and remove them when there's no pods running on them. Resource fairness, which is also very important for a multi-tenancy environment. And if you are using default scheduler, when you submit jobs, like in this example, we have 2 jobs. If you submit to the Kubernetes cluster with the default scheduler, and right now our cluster assume that we don't have enough resources for all the pods to be running. Assume we only have 2 slots for the pods, and then basically you don't know you cannot predict which pods will be running because the behavior is totally random. But if you're using YuniKorn instead, we were considering about the inter-queue resource fairness. You are doing the queue mapping from the queue to the namespace, which means between the namespace we have the resource fairness. And when we do the deployment, we're checking the resource fairness. This is a guaranteed resource. For this namespace, we are already using more resource than the guaranteed resource. And for this queue, we're not using that much. This is the guaranteed resource. We still have space. So that means this queue will get the resource first because we need to guarantee the resource used by this queue. And then in that case, if you submit the same jobs to YuniKorn, we can always get the same behavior. The B1 and B2 will be allocated based on the resource fairness constraint. So in this way, the behavior of the job allocation will be more predictable than the default scheduler. We have done some resource fairness evaluation. So we have done some tests with kubemark. We simulate a lot of nodes to test the throughput. So basically, this is not throughput, sorry. So this is a resource fairness evaluation. So to test the resource fairness, we have set up several queues, and each of the queue we submit different number of jobs, and each of the pod will have a different specification resource profile. When we submit them, you can see in this chart the resource usage of each of the queue will grow in a similar fashion, which means the resource fairness is being honored. This is the throughput. So for the scheduler throughput, we have simulated environment with kubemark. We have simulated 2,000 nodes and 4,000 nodes. We have tried to schedule 50,000 pods onto them. And the throughput we can say is this is the number for YuniKorn and this number for the default scheduler. And we can see we are more or less twice better than the default scheduler. And another observation is when we increase the number of nodes from 2,000 to 4,000, the performance, the throughput actually has a lot of regression. But that is basically due to the fact that there's some bottleneck in the API server. When the more number of nodes you have, the latency of the API server will be slower. So this is a detailed report. If you are interested, you can look at the detailed report there. We have a lot of how we run the information about how we run the tests, how we calculate results, and including all the results. So to deploy YuniKorn, I think it can be easily swipe the default scheduler. And because we support all the Kubernetes semantics, including the predicts, every predicts used today, it can be supported by YuniKorn, like the load selector, pod affinity, unaffinity predict, attention toleration. Those are very, very common. Every predicts are continue to work. And second is we also support PVC, PV, volume bindings, dynamic provisionings. Those are being tested for a long time, and they are working nicely. And also, we are publishing our K scheduling events to Kubernetes event system, which means when you work with YuniKorn, you will not find it very difficult to work with because you can get all the similar information from the event system. And also, it works with the cluster autoscaler. We were doing a lot of work on EKS and to make YuniKorn can work with autoscaler nicely to do the automatic scale up and down. And also, it supports the management console commands like you want to coordinate nodes, you want to add or remove new nodes. Those are all supported. There should be no gap existed today. And we also have a UI to prevent a central view for apps and the queues. This is a snapshot. This is a screenshot of about the UI, and you will see the applications. And for each application, you can see how many allocations for the application you have. Basically, we aggregated those pods into requests and groups them into applications, give people a better view about what's happening for their jobs. And also, we have the view for queues, and in here we can see the queue resource utilization and the capacity, total capacity, min and max capacity, used capacity. So every such information can be directly viewed from the UI. Then the last section is about the roadmap and the future. The project was open sourced at July 2019, and the project we have been entering into the incubating in Apache from January 2020, and 0.8. And this one, at the time we're speaking, we're under the voting phase, so it should be coming out in a week, less than a week. And this is a community effort by Cloudera, Alibaba, and many other companies like Microsoft Linking. We have a great community there to work together to figure out what's the best features we want to include in YuniKorn, and make sure YuniKorn can support the both long running and batch workloads for the multi-tenancy environments nicely. So for existing 0.8 release, we have already have these features shipped, including hierarchical queues, cross-queue fairness. We have fair, faithful job ordering policies. We have fair bin packing, no sorting policies, self-queue management, pluggable app discovery, which basically you can easily support other Kubernetes operators. We have the built-in metric system. We have the Prometheus integration. And for upcoming 0.9, we were going to support the gang scheduling and also the job task priority, the node sorting algorithm optimization, because we want to do more enhancement for the performance. And also we plan to add a Grafana plugin so user can get more detailed view about the metrics from the scheduler. Yeah, I guess that's all for my slides.